stratum basale. It originates from the stratum basale. That's why they call it basal cell. The cells in the stratum basale cause it. Caused by UV rays. It does not spread very often. It is not very metastatic. You guys know what metastasis is? Metastasis is when the cancer tumor spreads. Part of the tumor actually breaks off. It goes someplace else. It starts to grow. And it puts down roots. It starts to grow there. Some cancers spread really quickly because they're not held together very well. Other cancers don't spread very much. These guys, stratum basale, is usually encapsulated, so it stays put. So as long as you get it checked every now and then, you'll be okay. Basal cell carcinoma is not a bad one as long as you kind of catch it. Squamous cell carcinoma, that's the second most common skin cancer. That comes from the stratum spinosum. That comes from the stratum spinosum. It's a little scaly. It's like a scaly patch on your skin. And it will metastasize if not removed. It will metastasize if not removed. But as long as you're paying attention, you'll be okay. Melanoma comes from melanocytes. Melanoma comes from melanocytes. Melanoma is tough. Melanoma is tough. It metastasizes quickly and resists most chemotherapeutic agents. It metastasizes quickly and resists most chemotherapeutic agents. It used to be pretty much death sentence. You got melanoma, you're going to die. Especially if it had metastasis. They're getting better at extending the life of somebody with melanoma, but we're not anywhere near a cure yet. That's also caused by exposure to UV rays. We talked a little bit about this already, but you're down here in sunny Florida. We got to be careful about exposure to UV rays. Melanoma will kill you quick. The only way to not die is to catch it early. You can do this by applying the ABCD rule. ABCD rule. You should check yourself. You should check your loved ones. You should get your loved ones to check you. Anytime you see a new spot on your skin, apply the ABCD rule. Look for new moles or pigmented spots. A stands for asymmetry. A stands for asymmetry. If it's a nice little circle, that's one thing, but if it's kind of a weird shape, that's asymmetrical. That's a danger sign. You want to get that checked. B stands for border irregularity. You might have something like this. It's like indentations in the border. The border is not solid. C stands for color. If it's all one color, that's good. If it's multiple colors like dark and light, that's bad. If you see red or blue in it, that's really bad. And D is diameter. If it's bigger around than a pencil eraser, that's a a bad thing. Also, if it's changing, if it's growing, that's a bad thing. So check your loved ones, check yourself. If anything new pops up and looks weird, go get checked, go see a dermatologist, don't mess around, because this will kill you. On your notes it says A, B, C, D, E. E is like an extra one. E is elevation. If it's kind of standing up away from your skin, if it gets dome shaped or sticking out, that's another warning sign. Go be checked by somebody who knows what they're doing. Burns are really nasty wounds. Burns are really nasty wounds. You estimate how much of your body is burned using the rule of 9. The rule of 9 lets you take an estimate, a guesstimate of how much your body is burned. How many guys have read an article, they say 30% of the person's body was burned, something like that. Take a look at page 167. And there you'll see the rule of 9. There are 11 areas of your body. Each one is 9%. The remaining 1% is your perineum. That's not good to get burned either. If you're not sure where that is, take a look at page 167. Basically, the front half of your head is 4.5%, and the back half of your head is 4.5%. So if you get your head burned, that's 9%. If you get your head burned, you got other issues too. The front of your arm's 4.5, the back of your arm's 4.5, so each arm is 9%. Each leg is 18%. Front of your trunk is 18, and the back of your trunk is 18% of your body. So you can figure out what percentage of your body is burned. If you have burns over 40, 50% of your body, that is not good. You may very well not make it. Burns do a number of things. Burns lower your immunity. And they also remove the skin, which is protecting you from foreign invaders. So your immune system's on the fritz. You don't have any way to keep the nasty bacteria out of your wounds. Infection is a big problem with burns. If you look on page 166, you can see pictures of the different degrees of burn. When they talk about burns, they talk about first, second, and third degree burns. First degree burns pretty much only damage the epidermis. First degree burns pretty much only damage the epidermis. Most of you have probably gotten the first degree burn. What am I talking about? Sunburn, yeah. You get red, it hurts. That's the first degree burn. Second degree burns are when the damage extends down to the dermis. Second degree burns are when the damage extends down to the dermis. This is when you get blisters. Remember, blisters are where the epidermis comes away from the dermis. So you're pretty much through the epidermis down into the dermis, and then the epidermis is dead, so it kind of falls away, and that area fills with fluid. That's a second degree burn. You can get sunburn bad enough to get blisters. How many guys have gotten all blistered up from the sun? Yeah, that's a second degree burn. That hurts too. That hurts too. That's painful. It takes a lot of healing sometimes in the dermis. All right, fess up. How many guys like to peel skin from a sunburn? See how big a sheet you can get? Come on. Some of you guys do that. Yeah. Maybe it's just a guy thing. I don't know. Girls are like, ew. But it's kind of hard to get on. Third degree burns are also called full thickness burns. That gets down into the tissue under the skin. That's in the hypodermis and even deeper. Sometimes the skin literally falls away. If you see somebody who's just been burned, it looks like their skin is coming off when it is. Those are 3rd-degree burns. Learned a little thing about boats, had a pretty good object lesson. How many guys have a boat, or your family has a boat, you mess around with it, it's kind of fun, right? Careful, especially if you have an IO. You know what an IO is, import outboard, the motor's underneath the cover, and the outside comes out underneath. They have a thing called a blower, blows all the fuel fumes out before you crank the ignition. If you have an outboard, you don't have to worry about this. I used to have a boat up in Raytown Lake, Pennsylvania, and wife and I were sitting in the marina and watched this happen. Guy brought his brand new boat up to the fuel dock, put about 50 gallons of gasoline in it, except he had a 30-gallon tank. What had happened was the nozzle that connected the fueling port to the gas tank was off. He ran 50 gallons of gasoline into his bilge, started the motor, lit off, ended up blowing him over the front of the boat. There was all kinds of adventures trying to get the boat put out. I was helping because it was sitting there at the fuel docks burning, and we used all the extinguishers that were there and then cut it loose. It's a mess. Guy came out of the water, it looked like he had long pants on that were shredded. It wasn't, it was his skin. He got burned really badly, 3rd-degree burns. I don't know what happened to him after that, but they fierce rehab. Because the epidermis doesn't grow back. If you get a 3rd-degree burn, you need a skin graft to cover it. It's epidermis. If you get a 3rd-degree burn like this, epidermis is going to grow back over there. You got to put skin grafts on it. What they'll do is they'll take a little pillow, make a slit in your butt or something like that, put a pillow in there and blow it up to make extra skin. Then they put the skin through an expander, which looks like a cheese grater, and spread it out, slap it on there and grow it.
Did I miss it here that we get new skin every 25, 45 days?
Epidermis, not the dermis.
Oh,
The epidermis
okay.
recycles.
Okay.
Remember, stratum massalia is growing up like that?
So you burn the dermis.
Yeah, these are, you burn the epidermis, you burn the dermis, and you're down to the tissue underneath. And then that doesn't cover over, that doesn't heal over, that's too big.
Well, I guess it explains why this, it burns the cells too, the living cells in our skin.
Yeah.
Maybe that's the reason it doesn't grow up. I'm learning.
Yeah, you kill all the cells, and the epidermis isn't gonna grow back to cover that.
Yeah.
And and the dermis is gone too if it's a 3rd-degree burn. Just the stuff underneath.
Too, yeah.
So, don't get burned. Is the takeaway from all this. All right. Any questions about the integumentary system? I want you guys to take a look at page 168. It says system connections, basically integration with other systems. That's a good page to kind of take a look at. That kind of connects a whole bunch of different things you might not have thought about. I may grab the test question out of there every now and then. So, don't memorize blah, blah, blah. Don't make 3x5 cards and put flashcards on that stuff. But, read through it once or twice. That'll kind of hang around in the back of your mind, and that'll help you with questions. All right. Now on to bones and skeletal tissues. Pretty much everybody has at least started bones in lab, right? Anybody has not touched a bone in lab yet? Okay, good. Take a look at page 175. We're going to start with skeletal cartilages. Cartilage and bone are kind of similar. Cartilage and bone are kind of similar. They have widely scattered cells and a lot of extracellular matrix. They have widely scattered cells and a lot of extracellular matrix. In cartilage, the matrix is kind of squishy a little bit. Not super squishy, but sort of squishy. Like the eraser on the end of your pencil is squishy, kind of squishy. Bone is not squishy. Bone is hard, it's calcified. Bone will crush rather than squish. Three major types of cartilages: hyaline cartilage, elastic cartilage, and fibrocartilage. And I want you guys to kind of have an idea what we're talking about. So turn back in your books to page 135. Turn back in your book to page 135. There's hyaline cartilage. That provides support, and it's flexible, and it's a little bouncy. It's a little bouncy, and you can see those cells called chondrocytes in it. You can see those cells called chondrocytes in it. What do you remember about the word chond? C-H-O-N-D. That's the word for cartilage. A chondrocyte is a cartilage cell, right? Chondrocyte is also a mature cell. It is maintaining the cartilage around it. Chondrocyte is a mature cell. It's maintaining the cartilage around it. What's a chondroblast do? It makes cartilage, yes, making the cartilage matrix. Remember blasts are baby cells that make a lot of stuff? The chondrocytes are mature cells in cartilage. Chondroblasts are baby cells that make cartilage. Hyaline cartilage, they're collagen fibers, but they're pretty small. Collagen fibers, bless you, but they're pretty small. Can't really see them. Cartilage looks almost like milky white. You probably should shine some light through it if you get a bright enough light. The elastic cartilage on page 135 also is like hyaline cartilage, but it contains elastic fibers. It's like hyaline cartilage. It's got some collagen in it, but it also has elastic fibers. Those elastic fibers make it nice and stretchy. Those elastic fibers make it nice and stretchy. Ears are made of elastic cartilage. Go ahead and smush your ears up a little bit. You can smush them around and move them around. That's elastic cartilage. And if you turn to page 136, fibrocartilage has lots of collagen fibers. Fibrocartilage has lots of collagen fibers. Looks like the sky. Looks like the sky. It's not as stiff as hyaline cartilage. It's not as stiff as hyaline cartilage. Elastic cartilage is nice and mushy. Hyaline cartilage in your nose is kind of stiff. Go ahead and push on your nose a little bit. Now you guys have all seen a skull. You know there's just a hole there, right? I mean, this is not bone out here. This is hyaline cartilage. But it's pretty stiff. I mean, you can move it around, but you don't want to go smack like that, because it's going to hurt. It's pretty stiff. Fibrocartilage is kind of a little springier than hyaline and not quite as springy as elastic. Fibrocartilage is going to be found in your joints. I mean, in your vertebrae. I also want to introduce you guys to this concept. If this is a piece of cartilage, there are little spaces in there for cells. spaces are the lacunae, actually. Those are spaces, little pockets in the cartilage matrix. And there are cells living in there. Those guys are the chondrocytes. So those are chondrocytes living in lacunae. That's the way cartilage is, all three kinds of cartilage. Have lacunae, which are spaces, and they'll have chondrocytes living in those lacunae. They'll have chondrocytes living in those lacunae. That make sense to everybody? Okay. Let's go back to 175. You can see there's cartilage scattered all through the skeleton. Cartilage scattered all through the skeleton. And that cartilage grows. When you grow, the cartilage grows. There's two different ways it can grow. Appositional growth is kind of adding layers on the outside. Appositional growth is adding layers to the outside of the cartilage. If I got a piece of cartilage here, chondroblasts on the outside are going to secrete more matrix. They're going to secrete more matrix. Add another layer of cartilage. And then we'll add another layer of cartilage. And then another layer of cartilage. That's called appositional growth. That's called appositional growth. Kind of like layers on rings on a tree. You just add like a new layer of cartilage, and another layer of cartilage, and another layer of cartilage. That's called appositional growth. It's one way cartilage grows. The other way cartilage grows is interstitial growth. In interstitial growth, we'll have a chunk of cartilage here. And we'll have chondroblasts in here, and they grow. They grow and divide. It's kind of like blowing up an air mat. Kind of goes like that. It grows from the inside. That's interstitial growth. That's how cartilage grows. Bone grows that way too. Bone can grow on the outside by adding layers, kind of from the inside. The inside growth only happens when you're growing and you're getting taller. The outside, the appositional can happen when you start working out more. You can make your bones actually more solid, you can make your bones bigger. If you look at a professional tennis player's skeleton, their serving arm, the bones will be bigger than the other arm, because it's under more stress. We'll talk about this more, but if you look at somebody's skeleton, you can make a guess at what they did as a job, whether they work manual labor or some jobs leave permanent changes to the skeleton. I'll probably tell you this again, because I'll forget I told you this now, but when they excavate an old graveyard, especially over in England, they find a new graveyard that's 300-400 years old. They can look at the skeleton, and if you were a stonemason or a bricklayer, one side of your body is going to be much beefier, the bones are going to be much beefier, because of course you had to carry your rocks, you had to carry your bricks. They had these things called hods, which is basically a stick with a V shape, two planks like this, and you stack your bricks up here. Carry that around. You have to carry your bricks to where you were going to lay them. And the right side of their body, if they're right-handed, is going to be much thicker. The bones are going to be bigger because there's more stress on that side. Yeah, yep. So that's appositional and interstitial growth. Is everybody okay? Now, bone classification. Of course, we have to classify these things. Classify them a couple different ways. You basically have two different types. Well, let's say it this way. You have an axial skeleton and an appendicular skeleton. You have an axial skeleton and an appendicular skeleton. If you look at page 175, the axial skeleton is kind of orange. The appendicular skeleton is kind of tan. The axial skeleton is your skull, your vertebrae, and most of the bones attached to your vertebrae. Your ribs, your sternum, hyoid bone. Those are all axial skeletons. Appendicular skeleton is your arms and legs. That's your arms and legs. And the bones that attach your arms and legs to your body. The bones that attach your arms and legs to your body. Like your hip bones and your scapulae. What's the not so fancy word for scapulae? Short blades? Scapula is one of them, scapulae is two of them. What's a fancy name for your hip bones, your pelvic bones? Coxal bones, yes, they're called os coxae and coxal bones. They're actually three bones fused together. So that's axial and appendicular. Before we get any further, let's go back and take a look at the skeletal cartilage on page 175 before we navigate away from there. Hyaline cartilage makes up the articular cartilage that's found on the end of bones. Hyaline cartilage makes up the articular cartilage that's found on the ends of bones. Makes your bones move together nice and smoothly. We've talked about this a couple times now. That's the cartilage you find on drumsticks and chicken wings. Costal cartilage is also made of hyaline cartilage, and it connects your ribs to your sternum. Costal cartilage connects your ribs to your sternum. You can see those on 175 also. It'll really help you to look at 175, you can see all these things. Costal cartilage connects your ribs to your sternum, also made of hyaline cartilage. The respiratory cartilages, take a look at 175 upper right. Cartilage of the larynx, the esophagus, and the bronchi. All keep your airway open. Those are all made of hyaline cartilage. Those are all made of hyaline cartilage. And your nasal cartilage makes up your nose. That's also made of hyaline cartilage. Your nasal cartilage makes up your nose. Elastic cartilages make up your ears and your epiglottis. Elastic cartilage makes up your ears and your epiglottis. You guys know what your epiglottis is? Yeah, it's all flat. It covers up your trachea when you swallow. Does it work all the time? No. Sometimes it lets a little water through, a little juice through. What happens then? Coughing, hacking, sputtering, yeah. You want to keep that stuff out of your lungs. Has anybody ever inhaled like a piece of corn or a pea or something that gets out of your lungs? Sometimes that happens. You might want to go get it out, otherwise it grows fungus and stuff. Hopefully that's not you. And then fibrocartilage, you find fibrocartilage between your vertebrae. They're called intervertebral discs. Intervertebral discs in between the vertebrae are made of fibrocartilage. If you know somebody with a slip disc or a bulging disc, they can tell you all about how much that hurts. You also find fibrocartilage in your pubic symphysis. That's the place where your two pubic bones come together, the very front of your coxal bones. That's called the pubic symphysis. And in the meniscus of your knee, that's also made of fibrocartilage. Fibrocartilage is also meniscus of your knee. Anybody ever have a torn meniscus or know somebody with a torn meniscus? Yeah, that's not good. Alright, that's enough cartilage for a while. Let's go back to bone classification. Go ahead and turn the page to 177. We classify bones based on their shape. Long bones are pretty common in the body. Just about everything, well, most of the things in your arms and legs are long bones. A long bone is longer than it is wide. A long bone is longer than it is wide. You would all agree that the femur is pretty long, right? You've all seen a femur. But the little tiny bone in the end of your little tiny toe, it's about that long. Is that a long bone? Yeah, because it's longer than it is wide. So long doesn't necessarily have to be long. The long bone is just longer than it is wide. Short bones are usually shaped like cubes. It's like little blocks, little cubes. You find those in your wrists and your ankles. You'll find those in your wrists your ankle. What's the name for your wrist region, anatomic region? Carpal region. These bones are called carpals. What about your ankle? What's the anatomic? Tarsal. Those bones are called tarsal bones. Glad you learned those region names now. Carpals and tarsals are short bones. Sesamoid bones are shaped like, guess what? Sesame seeds, yep. Sesamoid bones are shaped like sesame seeds. A great example is your patella, otherwise known as what? Your kneecap. Your patellar region, right? That's a sesamoid bone. Sesamoid bones grow inside of tendons. Sesamoid bones grow inside of tendons. Some people have more than others. Take a wild guess and tell me what shape flat bones are. Flat. They're thin, flat, and usually a little curved. They're thin, flat, usually have a little curve to them. A lot of the bones in your skull are flat bones. A lot of the bones in your skull are flat bones. Also your sternum and your scapulae and ribs. Sternum, scapulae, and ribs are also flat bones. And then irregular bones, that's just everything else. Irregular bones are just everything else. Your vertebrae and your costal bones are irregular bones. Your vertebrae and your costal bones are irregular bones. Bone functions. If I ask you functions of bones, you think you can write support, protection, and movement? No. What are you missing? The second word, yes. Remember, 2 words, noun and a verb. So, you could say, bones provide a framework for your body instead of support. Say, bones provide a framework for your body. Bones cradle soft organs. Bones cradle soft organs. For protection, bones protect organs from impact. Bones protect organs from impact. What is the most protected organ in your body? Your brain. You have a bony vault where you store your brain away. Your brain is pretty soft consistence. If you opened up the skull and took all the membranes away, you could take pretty much a spoon and go like that and pull some of it out. It's kind of fatty. It's got some connective tissue holding it together, but it's a fatty mess. Kind of gross to see what hasn't been preserved. You guys are going to do sheep brains in lab. They're almost like rubbery because they've been preserved in formalin. But brains fresh out are mushy, very fatty. You guys ever had brains and eggs for breakfast? Yeah, it's, I don't know, I don't eat much organ meat. It's kind of gross. Brains are pretty fatty. But apparently, you put it in with eggs because you can't really tell the brains from the eggs. They can make nice sloppy scrambled eggs. So, next time you're at a restaurant somewhere and you see brains and eggs, try it. You guys heard of mad cow disease? Yeah. They're called prions, proteins. That was over in England, right? You know, if you were in England in the eighties, we still don't know if you're gonna have problems or not. You know where that came from, right? We were feeding sheep to cows. The sheep would die from a disease called scrapie. They called it scrapie because the sheep would just lean up against the post in the pasture and just do this and basically scrape their skin off because they were having neurological issues. So some genius decided, well, cows need protein too, so they fed the sheep carcasses, ground it up and put it in feed, and fed it to the cows. Well, that transmitted disease to the cows. And if you ever seen a movie or a video of a cow with mad cow disease, it's pretty horrible. They're total loss of brain function. They fall down and can't stand up and just, it's pretty horrible. But the good thing is that's not here in the United States, right? We don't have mad cow disease here, right? Wrong. Not so much in the beef population. I would not eat any kind of meat that has beef or pork or any kind of central nervous system matter in it. In the United States, we call it chronic wasting disease, and it's in the deer and elk population. So if you know somebody who hunts deer, I don't know if it's down here in Florida or not, but up north where they have real deer, you know, deer that are bigger than German Shepherds, you have to be careful, because if you eat any central nervous system stuff, or any fluid from the central nervous system, you can come up with chronic wasting disease. In humans, they call it Creutzfeldt-Jakob disease. Probably the same prion from species to species to species, and it's jumping around. So, you wanna shoot deer? Cool, eat them. I used to do that when I lived up in PA. I ate what I killed. I haven't done it since I moved down here, but you wanna eat deer? Cool. Don't have spinal cord and brain come in contact with anything that you're cleaning. Don't do it. All right. Oh, that was a little sidetrack. Where are we at now? We're still doing protections, right? Yeah, brain protection. Okay. Movement. Another category of functions for bone. Let's say bones provide attachment points for muscles. Bones provide attachment points for muscles. Mineral storage. This is an easy one. Bones store calcium. Bones store calcium. We're going to talk about this several times in this chapter. But I want you guys to think about bones like your calcium bank. Bones are like your calcium bank. Your calcium level is very, very important. Your calcium level in your blood is very, very important. Calcium is responsible for your heartbeat. Without calcium, your heart cells can't talk to each other and beat at the same time. Calcium is also very important for transmitting nervous impulses. Without calcium, you can't release neurotransmitters. So having enough calcium is really important. Having too much calcium makes your heart beat too fast. It causes other issues. So calcium is one of the things that is maintained by negative feedback methods of maintaining homeostasis. Calcium levels are very important. Your bones are your storage banks for calcium. Every day there are cells that put calcium into your skeleton, and every day there are cells that tear calcium out of your skeleton. You're constantly making deposits and withdrawals from your calcium bank. We're going to talk about that a couple times. So, calcium storage, mineral storage, is a really important function of the skeleton. one of the things that helped us leave the sea. Because when they were just sea creatures, you get calcium out of the ocean water. We don't have ready sources of calcium. You just can't say, oh, I think I'll download some calcium. Blood cell formation. Bones serve as sites for blood cell production. Bones serve as sites for for blood cell production. Yeah, bones are places where blood cells are made. Bones are places where blood cells are made. And if you already had lab, you may have picked up that spongy bone is where you make blood cells. Spongy bone is where you make blood cells. There's stuff called red marrow, where the spongy bone is. And that makes blood cells. Red bone marrow is making blood cells, red bone marrow is in spongy bone, which is inside of short bones and the ends of long bones and all places. We'll talk about that. The site for blood cell formation. Bones also store fat. Bones also store fat. Long bones are hollow. There's a space inside of them called the medullary cavity. And that's where you find yellow marrow, which is adipose tissue. Yellow marrow, which is adipose tissue. We talked about this in lab 2, but if you ever go to a steak joint and they have roasted marrow bones, try it. Kind of like meat butter, they give you the bone, they give you some toast points, and you spread it on. It's bad, but it's nice. It's got a good umami taste to it. It's savory, it tastes like steak. Alright, that'll work for functions of bones. Now, bone structure, page 177, there's a really nice picture. Shows you spongy bone and compact bone. Spongy bone and compact bone. Compact bone is a hard, smooth outer layer of bone. Compact bone is the hard, smooth outer layer of bone. Spongy bone looks like a sponge. It's a mesh of little bony needles called trabeculae. They're all interlaced with each other. They're all interlaced with each other.
What were they called?
Trabeculae. If you look on page 177, you can see it spelled down in the picture. All bones have a layer of compact bone on the outside. Short, flat, and irregular bones, they're all spongy bone on the inside. Long bones have a hollow medullary cavity. Now we're a couple minutes ahead in lecture. I told you guys about the crash course before. How many guys are watching crash course? Alright, I'm going to show part 1 of crash course the bones. Try and entice the rest of you guys to watch this and use it as a part of your regular study regime. If you don't know where search for a crash course bones, or a crash course anatomy and physiology brings the whole thing up.
In March of 2015, American astronaut Scott Kelly and his Russian colleague Mikhail Kornienko began an unprecedented mission in space. They began a 1-year term of service aboard the International Space Station, the longest tour of duty ever served on the ISS. Now, I imagine there's all sorts of stuff to worry about when you're packing for a year-long space voyage, like, say, how many books should I bring? How many pairs of underwear? Am I really okay with pooping into a suctioned plastic bag every day for a year? Will I come upon a derelict ship haunted by some stranded and insane astronaut from a forgotten mission, like in pretty much every space horror movie ever? Will there be coffee? Reasonable questions all, but in reality, another one you might want to ask is, will I be able to walk when I get back home? We know microgravity is hard on a body, and this mission is largely about testing the physical effects of being weightless for so long. Astronauts often experience things like trouble sleeping, puffy faces, and loss of muscle mass, but perhaps the most serious damage a microgravity environment causes is to the bones. And bones, well, they're pretty clutch. So they may look all dried up and austere. Don't be fooled. Your bones are alive. Alive!
By the way, that's one of the issues we're still facing for our mission to Mars. You guys, we want to go to Mars by 2020 or whatever. We still have to figure out how to get people in space for no gravity for 18 months and then back again and have them be alive when they come back, have them have bones when they come back. We don't know how we're going to do that yet.
If I tell you, they're actually as dynamic as any of your organs and are made of active connective tissue that's constantly breaking down, regenerating, and repairing itself throughout your lifetime. In fact, you basically get a whole new skeleton every 7 to 10 years. In short, your bones do way more than just providing your squishy sack of flesh with support and scaffolding and the ability to move around. Your bones are basically how you store the calcium, phosphate, and other minerals you need to keep neurons firing and muscles contracting. They're also crucial to hematopoiesis, or blood cell production. All of your new blood, and we're talking like 1 trillion blood cells a day, is generated in your bone marrow, which also helps store energy as fat. Bones even help maintain homeostasis by regulating blood calcium levels and producing the hormone osteocalcin, which regulates bone formation and protects against glucose intolerance and diabetes. So the big buzzkill about life in space.
By the way, that's another function of bone. Bone produces hormones. Bone produces hormones.
Is that up there? A person suffers 1 to 2% bone loss every month. By comparison, your average elderly person experiences 1 to 2% bone loss every year. So for Kelly and Kornienko, that could mean losing up to 20% over a year in orbit. Given everything your bones do for you, that's really serious. And while most of that loss is reversible once they're back on Earth, it's not as easy as chugging some Madame Pomfrey's Skelligro potion. Rehabilitation can take years of hard work, and that's after just a few months in orbit, which is why Kelly and Kornienko are heroes of science, and not just for scholars of anatomy and physiology everywhere, but for anybody who has bones. An average human body contains 206 bones, ranging in shape and size from the tiny stapes of the inner ear to the huge femur of the thigh. That's a lot of bones to keep tabs on, so anatomists often divide these structures first by location into either axial or appendicular groups. As you might guess, your axial bones are found along your body's vertical axis, in your skull, vertebral column, and rib cage. They're kind of like your foundation, the stuff you can't really live without. They carry your other body parts, provide skeletal support and organ protection. Your appendicular bones are pretty much everything else. The bones that make up your limbs and the things that attach those limbs to your axial skeleton, like your pelvis and shoulder blades, these are the bones that help us move around. From there, bones are generally classified by their shape, and luckily those names are pretty obvious. Long bones are your classic-looking dog bone-shaped bones, the limb bones that are longer than they are wide, like the tibia and fibula of your lower legs, but also the trio of bones that make up your fingers. Follow some of those long bones to your foot or hand, and you'll hit a cube-shaped short bone, like your foot's talus and cuboid, or your wrist's lacunate and scaphoid. Your flat bones are the thinner ones, like your sternum and scapulae, and also the bones that make up your brain case. And your irregular bones are all the weirdly shaped things like your vertebrae and pelvis, which tend to be more specialized and unique. But despite their variations in size, shape, and finer function, all bones have a similar internal structure. They all have a dense, smooth-looking external layer of compact or cortical bone around a porous, honeycomb-looking area of spongy bone.
How are you doing? How many guys think this is pretty good? How many guys might now start watching this stuff?
I just wanted to say that he moves pretty fast, but you can go into the slow down that video.
Okay,
because
yeah.
I don't know it, because he does have to.
Yeah, and one of the things that I do is I just watch it multiple times. If you watch this 3 or 4 times, you'll start picking up other stuff. How many guys saw the little drawing of the space station going behind his head? He was talking about the astronauts. Like this, and he's just talking, a little drawing of the space station, disappears behind his head and then comes out the other side. I mean, there's all sorts of funky stuff in here. You can slow it down, at YouTube, or you can, watch it multiple times. Either one, and why not both? Alright, so we got compact bone and spongy bone. Everybody good with that? Since this is up here, I'm gonna use this to fill out some notes. Gross anatomy of a typical long bone. We're gonna use his visual to fill out some of those terms.
This spongy bone tissue is made up of tiny cross-hatching supports called trabeculi that help the bone resist stress. And it's also where you typically find your bone marrow, which comes in 2 colors, red and yellow. Red marrow is the stuff that makes blood cells, so you should be glad that you have some of that. And yellow marrow stores energy as fat. If you happen to be a predatory animal, yellow bone.
Alright, let's slow down and read this. Bird bones are hollow, lightweight. They're just as much as a mammal skeleton. Mammals the same size. Compact bone is more compact and therefore denser. They might look thinner and lighter, but they're not.
Marrow.
How many guys heard that? Bird bones are hollow so they can fly. Common misconceptions in all kinds of science books.
Be one of the best sources of calories you can find. The arrangement of these bone tissues, though, can be slightly different from one type of bone to the next. In flat, short, and irregular bones, for example, these tissues kind of look like a spongy bone sandwich on compact bone bread. But in some of your classic long bones, like the femur and humerus, the spongy bone and its red marrow are concentrated at the tips. These flared ends, or epiphyses, bookend the bone's shaft, or diaphysis, which instead of having spongy bone in the center, surrounds a hollow medullary cavity that's full of yellow marrow. Now, although
Okay. We can fill out a couple things here. The diaphysis is the shaft of the bone. Diaphysis is the shaft of the bone. If you take a generic long bone, like this, and you cut it in half, you end up something looks like that, right? Everybody with me? This part here, that's what they mean when they say bony collar. It's like a ring of bone. How many guys have had an old-fashioned ham steak with the bone ring in it? That is the bony collar. The medullary cavity or marrow cavity is the hollow area in here. That's the hollow area. You can see it up there. It's got the yellow marrow in it. And yellow marrow is just adipose tissue. Yellow marrow is adipose tissue.
Now, even though it says it's hollow, it's just not soft or compact, but it's still totally with the bone.
Yeah, this marrow would extend all the way. When hollow might not be the best word for it, because there is stuff in there, but it's not bone. And if you take a bone out, and dry it out, clean it up, then it is hollow. That's what they're talking about.
Now, although bone can look rock solid, grab a microscope and you'll see that it's actually loaded with layers.
This, by the way, is spongy bone. Looks like a sponge, right?
Plates and laced with little tunnels. It's intricate and kind of confusing in there, but the more you zoom into the microanatomy of bones, the better you can see how they're built and how they function right down to the cellular level. Let's start with the basic structural units of bone called osteons. See?
Okay, let's go back to our notes. Diaphysis has compact bone on the outside, the hollow medullary cavity and yellow marrow. The epiphyses or ends of bone, that has compact bone on the outside and a spongy bone inside. that has compact bone on the outside and spongy bone inside.
For what?
Spongy bone in the epiphyses, compact bone on the outside. And this particular model here, this particular drawing here has a nice epiphyseal line. See this structure right here? This kind of line in between the spongy bone? That's called the epiphyseal line. The line in the epiphyses. What this is a leftover artifact from when your bone was growing. Bones grow from epiphyseal plates. If you are still getting taller, you have epiphyseal plates. That's how the bones get longer. We're going to get into this next class. If you have still growing, you have epiphyseal plates. Most of us have stopped growing. Probably pretty close to all of us have stopped getting taller at this point. That means our epiphyseal plates have turned into epiphyseal lines. Epiphyseal lines are basically the leftovers from our growth plates. So you guys know somebody who broke a bone at a growth plate. Yeah, then they gotta be careful, they gotta stitch them together and screw them together, because if you mess with that, the bone stops growing and then one leg's shorter than the other, one arm's shorter than the other. So these are epiphyseal plates, or epiphyseal lines, depending on whether you're growing or not growing. And see this little blue line out here? That's a good representation of the articular cartilage. They may get into it a little more. Let's continue to play this out.
Honeycomb-looking area of spongy bone. This bones, the better you can see how they're cylindrical weight-bearing structures that run parallel to the bone's axis. Look inside one, and you'll see that they're composed of tubes inside of tubes, so that a cross-section of an osteon looks like the rings of a tree trunk. Each one of these concentric tubes or lamellae is filled with collagen fibers that run in the same direction. But if you inspect the fibers of a neighboring lamella, either on the inside or the outside of the first one, you'll see that they run in a different direction, creating an alternating pattern. This reinforced structure helps your bone resist torsion stress, which is like twisting of your bones, which they experience a lot, and I encourage you not to imagine what a torsion fracture of one of your bones might feel like. Now, bone needs nourishment like any other tissue, so running along the length of each osteon are central canals, which hold nerves and blood vessels. And then tucked away between the layers of lamellae are tiny oblong spaces called lacunae. As tiny as they are, these little gaps are where the real work of your skeletal system gets done, because they house your osteocytes. These are mature bone cells that monitor and maintain your bone matrix. They're like the construction foreman of your bones, passing along commands to your skeleton's two main workhorses, the osteoblasts and the osteoclasts.
Okay. We're getting a little out over our skis here. Let's go back to articular cartilage. We've been down to epiphyseal line and epiphyses. And we're going to talk about articular cartilage. Y'all with me? Articular cartilage is the thin layer of hyaline cartilage that covers the ends of bone. Articular cartilage is a thin layer of hyaline cartilage that covers the ends of bones. More specifically, where it is places where bones move together. Places where bones articulate with each other, where they move against each other. That's why they call it articular cartilage, because it's where the bones move or articulate with each other. And that, of course, again, is made of hyaline cartilage. That's made of hyaline cartilage. Alright, so that's probably enough for today. Have a good weekend. You got one more week to go before spring break. Live for you.